So there's just like how to play through GNU. Okay. Basically all kinds of nowadays your machines. Okay, except Windows. Okay. All the libraries core. Okay, most of them are coming from the GNU project. GNU open source project, and many libraries are coming with that license. So this is a representative of the Moscow, and also this Linux, the Moscow again. Now, when they come together, basically, I will disclose to you their relationship, and I will classify their relationship in only in one way: the core properties, whether it's a library call or a system call. Okay. So let me tell you some secrets after you have done assignment one. Okay. So assignment one, when you do it, you need to call pipe. Remember this. And after you call pipe, the tutor tell you that hey, do the pipe before false. Okay. And also, if you try to print out the arrays, okay, there are two numbers coming from the top system call, and the two numbers seems to be always 4 and 5. No, 3 and 4. Always 3 and 4, right? So today I'll tell you what that. Okay, why is it 3 and 4 and then the next call is 4, 5 and 6. So it's over. Okay? So this is why is it going to be down? Is it darker than normal? Yeah. But I cannot change the outside, right? I can only change my inside. Okay. Don't worry, yeah. Here is a flowchart. So what is a flowchart? I will say that I skip the library call first, the fopen library call. I basically will later add factors. Fopen library call will call open. So you remember this. And inside open, what is going on? Open, if you have in our tutorial, where our tutors talk about it. These are tutors talk about it, the standard input stream, standard output stream, and standard error stream. And their numbers is 0, 1, 2. No? Oh my god. Then how come we can complete assignment 1? Okay, don't worry. So here is an array. I've already told you back in chapter 2 that there is an array of open files. Now for most, okay? For most of the process, it will have this 0, 1, 2 there. So where can you find them? Where can you find them? Now, if you have a Linux, you can do the same thing with me together. Okay? So what is the same thing? Inside Linux, okay? So remember, if you have a Linux now, or you already get SSH there, now do this. You don't need to do this, okay? This push D is for myself. Okay? So you should CD to here, PROC, okay? And then what? I just choose run a cat, okay? And suspend it. Okay? You follow the same way, okay? Follow the same way. Okay? And check the PID of this cat. Okay, can you do so? Run a cat. Don't do it on Mac. Mac is different. Okay? Call a cat, suspend it, and have PS to read its PID. Now, are you inside this PROC? CD to this number. Yeah. CD to this number. LS. This are most of the. You don't need to take a picture. I already recorded this. Yeah, you can convert to YouTube. So these are the bunch of kernel data structure export as files to you. Export as files to you. Now today I'm talking about file system. So I will CD to FD. So FD is a open file, list of open files of this process. LS. Now contain 3 numbers. So what are they? It's point to somewhere. It's point to the terminal. 0 is standard input. 1 standard output. to standard error. Okay? So I do another thing. So if you're following me, you can do the same as I doing. So I CD back to the PROC. Okay? Of course, kill the cat. And still remember the previous PID, okay? The PID is already on the screen. CD back to there. Doesn't exist anymore. So that means this is the cat process internal status inside the kernel export to you. Once this PID is being killed, then directory is gone. Right? So I do another thing. Still run cat, but try to redirect its output to somewhere else. I redirect it to here. Okay, txt.txt, okay, don't worry about that. So it means that while the cat is running, all the output will send to this file. Okay, and you already know what is the meaning. The meaning is the standard output is mapped to this file. Okay, so that I suspend it again. PS, this is the cat. Again, CD to the directory. Now the process is here because it's already also the suspend is also a status that you keep inside the kernel, right? Although it's suspended. CD to FD, still free, guys. Who is different? Do you understand now what is the meaning of map the standard output to a file? The open file inside the kernel data structure tell you that 1 is the standard output. It is no longer point to this PDS/0. PDS/0 means a terminal, your shell terminal. Now, input is point to the terminal, standard error also point to the terminal, not the standard output. Standard output point to elsewhere. Okay? Now, I love this arrow very much. What is the meaning of this arrow? Now we can go back to the PowerPoint. Okay. I forgot that. I usually do this, okay? After I do demonstrations, suspend something, send a while loop, okay, I forgot to kill them. I kill them. Okay? So, go to the PowerPoint. This is what I mean here. This array. And as a matter of fact, we can queue in this array context, okay? I basically forgot to tell you you can debug in this way. Yeah, if it is a pipe, it's no sense, right? But it is doing redirection, this makes sense. Oh, where I successfully map the file to that file descriptor. We call it file descriptor, this number. Okay, remember 0, 1, 2 usually is being hard code. Okay, for standard, later I will show the numbers and its name. Standard input, standard output, standard error. So who is the number 3? Usually number 3 will be your first open file. Usually your first open file. Okay, so the process is like this. The process is you send the file name to the kernel. The kernel will go to the hard disk to look for it. Let's say I open hello.txt. After I have this queue it because there is a file system if you are HFS plus, okay, doing the functions, FAT32 doing the other functions, but we never teach this before, so I only put a box here so that it is FS specific operations or functions. Then after it, I get the results. And the results is telling me several things. Does it exist? If it exists, okay, what are the information? Now remember, open a file doesn't relate anything to the data of that file. In this flow, you cannot find me saying the data about this file. Usually, I would look for whether it exists or not. Okay, if it's not exist, now depends on your opening mode. If your opening mode is read-only mode, I will give you an error. If you are opening a write-only mode, the fopen, okay, then I will create a file. So it doesn't mean anything related to data block. Now data block is a data thing. Okay? So then I will send to the kernel. Then I successfully found this file. I create a structure for it. Basically, this structure is concerning some of the things that you have seen in the directory called PROC. Okay? like whether this mapping is successful or not, okay, whether the file that you open, okay, is starting the location at 0 or 1 or 2 or 3 or 4, okay. Then I will do the last thing, map this global, really global, okay, a global array of open files mapped to your process, such that when process A open hello.txt and open another process open hello.txt, they point to the same guy. Okay, so this is global, and you only map a number inside your process, and this number 3 will be returned by open. Okay, so why pipe always give you 3 and 4? It means the pipe system call once it's finished, it creates 2 slots here, 3 and 4. Okay, and what I just said, what is the meaning of the meaning of a global structure containing all the files is like this. Let's say this purple guy is shared by 2 processes. The same file being opened by 2 different processes. Okay, this will be exported maybe to the 2 processes of different file descriptor, so that to you you see something different. To you see something different. Okay, maybe your file pointer. Yeah, file pointer is very interesting concept. Okay, the file pointer, that means the location that you have on the file. This guy may be different from this guy. No problem. No problem. Okay, because there is another structure here to governing that thing. Okay, but how about is real body? The real body is shared, and that's why in your assignment 1, you call pipe once, and 2 processes can see this. It's because of this. Because of this. Yeah, only one instance, you can create one instance of pipe, give you 2 ends, 2 ends can be shared to different processes. Okay? So this is the reason. Yeah, I know it's a little bit complicated. Okay? Now I give you something easier. Okay? So let's say this process ends, I return you number 3, I return number 3. Now what is the relationship between this number 3 to fopen call? Now first, fopen will call open. Okay, fopen is not a system call. So you want to open a file, call open. And where is this 3 goes? Basically, you are being cheated for at least, no, the first year you start writing C, the second year you write C, right? You're being cheated for more than 1 year. This file, remember how to write such a program? No, I don't expect you remember this. Okay, so you will write this or this. Which version? Line 1 or line 2? Line 2, right? You never write in line 1. Okay, so why? Why? You are being cheated for a very long time. This fopen silently call malloc. It silently call malloc, create a bunch of memory, really a large bunch of memory, and give you the pointer generated by the malloc call. Okay, so that's why when you call fopen, you will receive that using the pointer. It's silently call malloc. Okay, so why is call malloc? Well, at least maybe it needs to save this number 3, right? But fopen is not simple. Fopen contains anything other than this number. Now, let me tell you how to access back to this number. There is actually a call. Yeah, our tutor should teach you this, okay? Not telling you to remember, or 0 map to 0, 1 map to 1, okay? There is a call of file number. So what is the meaning of file number? Where is my terminal? Okay. So the file number.c is like this. So do you know what are the variables here? Standard in, standard out, standard error. Do you know what is this type? No, you don't know, right? File type. To be exact, pointer to file. Okay, these are 3 pointers. 3 pointers. Once you include standard io.h, you will have these 3 pointers. Okay, and these pointers point to your standard input, standard output, and standard error. Okay? So when you have this pointer, you can use a call for file NO or file number to QA as file descriptor number. Okay? So I have 4 calls here. The last call, I do it on purpose. I try to prove to you that 012 is being used. Now the next available number will be 3. I use Fopen to open a file in this location using the W, right only, so I should have the permission and it's always successful. It should give me 3. Okay, so let's go. See, the last guy is 3. The first 3 guys, 0, 1, and 2. Okay? So now, if you can roll back a bit, okay, the memory back in the 4 days ago, while you're doing debugging, what are the 0, 1, 2? Basically, along those 2, you only play 0 and 1. They are these 2 numbers. Okay, they are these 2 numbers. Okay? So they are all file pointer structure. Okay? Now, what's next? Next is why the file structure needs to do malloc. Because it's basically generate a huge amount of memory for one file open action. And the action is to give you one thing. We call it IO buffer, not buffer IO, okay? Buffer IO is there. No buffer there. Buffer IO is to describe what the file structure is doing. Okay, inside the file there is an IO buffer. And why there is an IO buffer? Is it about efficiency? Now I tell you what is this. If you understand this, it helps you a lot in debugging. Okay, so let me show you what are the read-write system call. I guess in assignment 2, you may try to use read-write system call because they are beautiful. Why they are beautiful? Now, what are the most call you use? Okay, you use fgetS, right? You know how to use fscanf, okay? But you never call fread and fwrite, right? I know that you never heard of it. Fread and fwrite, what next? Okay. So let me tell you, there are 2 system calls to read and write data, and they are the only 2 system calls to read write data, no more. So all those fread, fwrite, fscanf, fprintf, any others? fgetS, getS, putS, fputS, okay? All are they according to these 2 guys. There are only 2 calls. Now these 2 calls, okay, work with that way is to pass in a file descriptor. You open a file descriptor, okay, or you have open a file, and you put it's file number, okay, put in here. And its way to do it is very interesting. You give it a buffer, void type, so that means that it can be any kind of buffer. You can create an array of bubbles, no problem. You can create an array of char, array of integer, no problem. And the way to read things is you give me a buffer, tell me how many bytes to read, I will give you exactly that amount of bytes. Oh, okay. So that means if you call, what is that? Fscanf, first, and I will read the file, okay? Fscanf, you ask for a number using %d, and you set a buffer. Okay, I know you don't understand what I'm saying. Yeah. Okay, so let's say that I have this thing created, okay, and you call fscanf, f3, %d, and number, okay. Let's say the number is integer. Okay, so how many of you don't know about this? Okay, thank you. You all know that. So basically, if you translate this into a read call, what will it be? Yeah, fscanf is to look for an integer in the number input, okay, and put your data inside this 4 bytes variable, okay. In this 4 bytes variable, if you try to do this translation in your head, maybe it becomes something like this. Maybe I just say maybe. This buffer will 40 that number that I created for 4 bytes. And you try to read 4 bytes. Am I right? Maybe yes, maybe no, right? It depends on what is coming from the file, right? If the file gives you characters, then it's not correct. Okay? If give characters, not number. Okay? So just to tell you that the translation is quite complex. Quite complex. So don't directly map it, oh, Scanf like this, so does it mean that I want a number, which is 4 bytes, so you put in 4 bytes here and copy the 4 bytes into the no. Okay? And other version, and the reverse, the right call is you give your file descriptor, that means the open file, then you give a buffer and ask for how many bytes you want to write to a file. Then you will write that to a file. Now with this read-write call, I tell you, it is extremely fantastic. How to use read-write call efficiently? You can basically save some status of your program. Let's say inside your program you're doing something, you have an array of numbers, you want to do a checkpoint. You're going to do a checkpoint. You can say, let's say there are 10 elements of that integer array, so 10 elements is 40 bytes. You can set this buffer to be that array and write all 40 bytes there. That means that you back up your array using write call. Yeah, this is fantastic, right? While you're doing sorting, okay, you're afraid that you'll do something wrong. Okay, I use write call, back up the entire array into a file. After you finish all the things, use read. Read is to give a buffer address and you crawl a series of bytes and you ask for 40 bytes back from that backup file. Read it back and your array will back to life. I always use this to back up something. Yeah, I mean back up in the sense that I may try to Control-C my program, or Control-C program, all memory will lost, okay? So basically I can use these two guys, the write call, back up all the data into a file. When I need to reborn my progress, okay, I will just get it out from the file. You never think of this way, right? Because you're like, okay, wrong, again, we do it. And in Cantonese, yeah. This doesn't make sense, right? You can back up. You don't know that you can back up. Okay, don't worry. I tell you now, you can back up. Okay, remember this. Now, what are they? We call it system level or unbuffered I/O call. What is the meaning of unbuffered file? You have the name buffer here. The buffer means that here, this buffer means that it will get the things out, and they are raw data from the file. They are raw data from the file. Okay? And it's different from this guy. This guy is not reading raw data and give you raw data. No. Why? I input a stream of data, which is a string. Character 1, character 2, and character 3. It won't give you character 1, character 2, character 3, but give you an integer 1 to 123. Is it raw data? No. It's being processed. It's being processed. You take out 3 bytes, character 1, character 2, character 3, and it's transformed. This code, transform it into 123, put into your number. Now, get a difference. The previous read-write call is giving you raw data. What you inside that variable, the array, write it to the file, and you get it back from the file. Now this is not raw. It's being processed. And how is it possible? Okay, let's look at how many are being processed. Process here is this guy. Fflush will also do the processing. Okay, you try to Fflush to a file. We have an integer 1, 2, 3. Okay, and the integer 1, 2, 3, you want to print it to the file, it will 3 bytes, or 4 bytes. The 3 bytes are integer 1, character 1, character 2, and character 3. Okay, so they will do some transformation. And how is it possible? It's possible because inside the Scanf, Fscanf, printf code, inside the code of this code, they know that they can use, I should have used fpref, okay? Fpref maybe, okay? You see fpref, I pass in this guy, right? The fp, okay? Basically, the fp has a buffer to store all the raw data, okay? So the raw data is coming from here into the fp or into your standard IO stream. And this is scanf call. Scanf asks for %d. So scanf will do this. Hey, reach some call. Get me raw data first. I want character 1 and character 2 and character 3. Okay, they are in. They will save this raw data into the file structure. Yeah. And then use the raw data to the processing, transform character 1, character 2, character 3 into integer 1 to 3, and write it here. We call it buffer IO. Yeah, we call it buffer IO. And this is not the only reason for this buffer to exist. Yes? I don't understand. ATOI. It depends whether you call ATOI. You call it A2I, right? It's not exactly like that. Not exactly like that. The scanf call contains will become common codes with A2I. If A2I has some codes, scanf you do a %d, it will call A2I's code. But it doesn't make this shouldn't make sense up, right? Because it needs to read the data from the file first. And who should hold it? Right? You use A2I, you need a string buffer. Right? And the string buffer is actually hidden inside standard IO stream. Standard input stream and standard output stream. Okay? Standard input stream contains a buffer, we treat it as a string called A2I internally, then give you the things. So basically what you are saying there is if you call A2I by yourself, that means you use, not use, you emulate all happens inside scanf. Any questions? Now this is a boring beginning. Okay, again, thank you. I said yes. Okay, I hear you say yes. Okay. Now here is another example. Okay. Now there is something non-trivial. Non-trivial in the sense that you may not aware of it. Okay, you need someone to tell you. So what are this? Now I type 1, 2, 3, then it's transformed into 123. Okay, but how about I type 1 space and then 2 space and so on and so forth? What happened? If I do this, so you don't need to look at this part. Okay, this part, close it out. Okay. I mean this part, this code, this part. Look at this part. How many numbers will print if I input this line? 6, right? No 7, because if it continue, okay, you find that the input is only contains 6 numbers and it stays there because of the scanf call. Now I tell you a secret. The secret is, does this loop, okay? Now you tell me that you print 6 line, right? 6 numbers. Does it mean that inside here I call 6 times the scanf? Does it one-to-one corresponding to reading the raw data using read system call for 6 times? Maybe yes, maybe no, or who cares? Okay, but I tell you no. Usually it's only 1 time. Usually 1 time. And usually I didn't look at the library code. The library code, I guess, would be like this. You call for the first time, you call scanf. Then I will call read system call. And I will call 4K of data from the keyboard. Try to get as many as possible. Use 1 call only, get 4K. But I don't have 4K data. I only have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. 11 bytes, okay? I only have 11 bytes here. So, no 4K, don't worry, I get 11 bytes already, and put that 11 bytes into this raw data buffer, and let the scanf to query them one by one. Why do we need that? It's because usually when you call read system call, the device is much slower than your I/O device. I mean the memory. I mean, you work in memory is faster, and you work with a device is slower. So why not we just spare one slow call? Okay, we tolerate that you are slow, but I only tolerate you once, not 6 times. I tolerate you once, get all data up, put into this raw input data buffer, and you process it, and after you get this line, the Scanf will process it one by one in the memory level, much faster. And this is what we call the true meaning of buffer I/O, because of speed. Okay? So what is the time? Okay? The flow is like this. I don't know whether it's about input or output, okay? But both input output has this kind of buffer. Now this flow is about get char. Get char is input, right? Input buffer. So the get char is also doing the same thing because get char is more easy to understand. You want 1 byte, okay? I give you 1 byte, okay? But in a real scenario, when you call the get char, the first time you will look for the buffer, okay, the case 1, that means whether you are empty or not. Okay? I don't know. Let's say it is not empty. Let's say it's not empty. Then it will use the data inside the buffer. As the previous case, I guess it's 4K data. So you take the 4K data, put in the buffer, then you can look for characters 4,000 times. Okay? Then what if case 2, the get char call find that the buffer inside the file structure is empty. It's empty. Then it will call read system call. It will call read system call and grab another 4K data up and put it into the file buffer. Put it there, put the data in there, and let the get char to do the character processing again. So you won't find it slow. Usually, when the first time I talk about it, if you're aware of what exactly get char is, you will ask the question, maybe it's slow, right? Why do we get a bunch of data out? But while you're really working on it, you won't find slow. Because this is the way to speed up the whole process. Okay? And I know that you don't know what I'm talking about. Yeah. So I give you some code and then go back a little bit. Okay? I will go back, don't worry. I have a program here. You don't need to look up these 3 calls yet. Look at this program. This program is like this. I will print hello and slip 1, but character by character, and do a new line at the end. Okay? Now I have 3 versions of this implementation. And by treating this set v buffer call, now I show you the output first. And then I will explain what it is. It is set v buffer. Nope. Where is it? Oh, I separate that. Okay, the first example is called no buffer. Okay, basically I disable the buffer I/O. So what will happen? And that. Okay, do it one by one. And for output buffer type, we have another kind of buffer I/O. We call it line buffer. So what is the meaning of line buffer? The file structure will do this. Accept your input that I eventually will put on the screen, but I will wait for your new line character. Wait for 5 seconds. Boom, come out. Do you know what I'm doing? I'll show you the code again. Right, buffer.c. So you don't need to worry about what this is about. This is to set it into a line buffer. And I print 1 character, sleep, print another character, sleep. So you will wait for 5 seconds, and then suddenly I output new line. The output buffer knows that, this is new line, so I flush all the output to the screen. Again, 1 second, 2 seconds, it's too fast, or 4 seconds, or okay. Last one, full buffer. I call it full buffer. So what is full buffer? Full buffer has only two conditions that it will put the thing out to the screen. The first condition is the buffer is full. Second condition, the process is about to die. Okay? Nothing. Can you see the difference between the line buffer and the full buffer? Okay? Now remember line buffer. Yeah, I know it's boring, okay? 5 seconds, and then 5 seconds show the new line, and then dies. 1, 2, 3, 4, 5. Oh, sorry, this line, okay. Full. 1, 2, 3, 4, 5, 6, die. Quite good. Can you sense the difference? Can you sense the difference? Can you sense it? The full buffer, when it comes to the screen, it's basically because the process died. All those 1, 2, 3, 4, 5, 6 characters will be printed out immediately for the full buffer version. And the line buffer version is this 1, 2, 3, 4, 5 character buffer, and then I found a new line, so I flush the data out, and then wait for 1 more second, die. Does it sound familiar? If you have written a program in other operating systems, and I don't know why the current Linux is something different, okay? You will find that if you don't call Fflush, sometimes, okay, your shell prompt won't come out. I don't know whether you have tried or not, okay? So this is about the buffering, and we have three kind of buffer. One is called full buffer. I already tell you about it. Line buffer and out buffer. Write code behave the same. Write code behave the same. Okay. I mean, no write code. F write code. Okay. All things related to the write. If you work over the file buffer, then it will do the same thing. Okay. Now, what I'm going to show you next is I have to run it first. Okay. I run it first to prove it. Okay. What happened to my terminal? Dies. Wait, come on, baby. Oh. CUHK network sucks. Network. Still connected. EDU wrong. Come on. No problem. Okay. Suddenly back to life. Okay. So let me try this. Good. Still okay, huh? Very nice. Okay. Now I tell you one thing. By default, printf is using write call. Okay. Printf is using write call. Understand this. And printf is to work over a buffer because this is you are using the standard standard output buffer to flush it out. Now, the one more thing is standard output is line buffer I/O. If you encounter a new line, it will print the things out. If you don't encounter a new line, nothing will be printed out. Now, I want you to look at this program. Okay, this program, you already know what it is. So this is the program. Can anybody explain to me why we have two hello? Yeah, I hear it. The first time I see program, I suddenly worry that, do I need to design and tell other people that I teach OS wrong? Fuck, duplicate what has happened before? Is it too horrible? Before I teach, just before I on call, I guess everyone will be posting this onto the Facebook group and said that, I found a bug in Linux. Yeah, this sucks. And later you will find, oh, Mac also sucks. And then Windows sucks, everything sucks. Know why now? Because of the buffer. Because of the buffer. The buffer, remember, buffer is something related to memory, right? I always say buffer, but basically it's a piece of memory on the user level space memory. And this piece of memory will be duplicated while you call fork. And once you call fork, that means that the hello is inside the buffer, not flush out. What will happen? You will duplicate this hello into another new process, and when the new process and the old process together call new line printf, both line flush out. Now, if I edit the program like this, okay, I can't, okay, this one. Then, no problem, right? No problem. One line of fork, two line of new line, very clear. Yes, I change it back with the new line. Make, run, too hollow, very horrible, right? So, how many of you have seen this code before? How many of you have used it? Only you. A very few, okay? So you guys have used it, okay, also you. How many of you have seen this? Okay, you guys know that, okay, before it. Okay, some of you have seen this, okay? Oh, you also seen this, okay? Okay, you want to ask questions? Oh, because the standard output stream by default is line buffer type. By default is line buffer type. Default line buffer. That's why it didn't encounter new line, it don't go out. Or there's demonstration to illustrate different kind of buffer operation mode. Okay? So you have seen before. Now for those who have seen before and who have used it before, tell me what will happen if I write this code here. What is the output? And then I will explain to you what is Fflush. What will be the output? One hello and then two new line. Let's see whether his answer is correct or not. One hello, two new line. Okay, he got the answer. So what is the usage of Fflush? Fflush means that basically you need to know there is a buffer in order you can understand what is Fflush. Fflush means for things that is still hidden inside the IO buffer, please clean them out. Okay, so this is a mark. Put it there. I don't care what is inside. Flush it out. Okay? So I don't know whether you have tried before. Okay? This year, I don't know why no one asks questions. Usually, every year people will ask questions. The question is, my program has segmentation faults. And the program behaves very strange. It won't print anything before segmentation faults. No one tried. I know. I will do it now. No one knows what I'm talking about. Yeah, I feel sad about this. Okay, so I write a rubbish program, really rubbish. Now you will see how rubbish it is. Why? What happened to me today? I always swap the input order. What happened? Because now, okay. Okay, make sure you know. What will be the outcome? I give you 1 minute to discuss with your neighbor. Okay, I will run the program. I give you 1 minute. Okay, I don't want to disturb your eyes, okay? I'll remove this new line. Interesting. What is that? Oh, by the way, tell me, will you see hi-hi? No, okay? So this is a good program. I never see hi-hi. Okay, now I run it. Yeah, this code is interesting, but rubbish. Run. Where is he? Where does it gone? And then you will say that, oh, I discovered a bug in Linux. Yes, I hear one answer. And people think that it is abnormal. So everybody accepts it's normal. Yeah, you don't need to explain why, right? Why is that? Why I cannot see he comes out. You don't know, okay? Any people know this? Why there's no he? Don't know? No new line? Okay, so I satisfy your wants. Yeah, some people answer me that, oh, there's no new line. So I add a new line here. Do you think here? Make rubbish. Oh, this time we have he. Oh. Remove it. No he. Why? Tell me why. I already hear one answer. But by the way, do you understand what is segmentation faults? This will generate segmentation faults. Okay? Don't think that buffer IO cause that segmentation fault. Okay? The segmentation fault is because of IP reference and null pointer. Okay? IP reference null pointer so that I deserve to have a segmentation fault. Why I put a segmentation fault here? Because I want to generate one very common mistake or a very common phenomenon while you're doing debugging. You print something out, okay? You print something out, continue to print data out, I don't know, file or screen, and suddenly your program dies. Because of segmentation fault, floating point exception, or I don't know what kind of exception. That exception means the CPU caught an error, the kernel want to kill you. Okay? No one can stop this. It's unlike return zero. Return zero is something that we can stop. We're not able to stop. We can understand what is going on. But segmentation fault is something that you cannot stop. All the things inside the IO buffer will be kept there, and boom, your program dies. All gone. Okay? So this is very common mistake or common error. Okay, then while you're doing an assignment, okay, suddenly, oh, why there's nothing there? Okay, although a program dies, I know that it dies, but where are they? Where are the data? Still inside the process memory. Okay. So if I were you doing this kind of debugging, okay, please either put a new line. You don't want new line, okay, and flush them out. Okay. Now if I flush them out, then no problem. We'll see he segmentation faults. Or I can change a bit. It's not a segmentation fault. Yeah. You don't understand what I mean? Not and it's not a segmentation fault. Very clear. Now you understand what is file now? Very clear now. So basically, you are being cheated a very long time. That I will say that it's not because of C. It's because of the design of the library. Okay? And it will happen no matter what programming language you're using. Because all other programming language will rely on IO streams. Okay? So whether you are doing Java, Python, Perl, Ruby, whatever things you can call, once it calls standard IO streams without calling system call directly, okay, you will face this kind of rubbish code or rubbish results. Okay? So remember this, very well experienced. Now let me explain 3 more graphs. Okay, and then we have a break. What is this 3 graphs? Okay, I have 2 programs. Now these 2 programs will teach you 2 things. First of all, how to call system call read. Okay, how to call system call read. System call read here, I will try to read things from standard input. So I don't need to remember the file descriptor number of this guy. I call file number and put the number here. And what is these 2 guys? These 2 guys, if you can remember the read call, this is the buffer, and this is the size of, or not size of buffer, it's the number of bytes that you expect. So I do something crazy. I don't need an array to become a buffer. I just use a variable and use the address of that variable to pretend to be a buffer of 1 byte size. Okay? So this is the first thing that you will learn from this program. And every code is similar. Okay, I don't want to repeat the things, but every is a similar call but library level. Okay, if it's library level, it's use standard input. That means the contrast is this program is buffer IO. This program is unbuffer IO. System call is unbuffered. Library call is usually buffered. Now, what is the difference? Okay, so these 2 programs, I will do the following. I open a 1 GB file. Then what? Then I will try to read this 1 GB file by tuning my buffer size. What is the meaning of tuning my buffer size? I tune this area. I start with 1 char, and then 2 bytes buffer, 3 bytes buffer. Of course, I'm not doing it that way. I do it step by step, like 10 bytes and then another 10 bytes and 10 bytes. So it will start with 10 bytes, 20 bytes, 30 bytes, 40 bytes, so on and so forth. Okay? For this version and also for this version. Okay? What I'm going to show you, although it seems that I call the number of cores with increasing number of bytes that I will read in. So what will be the result? The number of cores will become fewer and fewer. Right? The number of cores become fewer and fewer. Say you start with 1 byte, but this is 1 GB file. You call it 1 GB time. 2 bytes, half the number of cores, and then 10 bytes, 1/10 of number of cores. Here we also have the same effect. Okay? But because of the buffer, you can see something very interesting. This is the graph. Okay? So I put an extra here, so it's not going to appear in a final exam. This, why is this green? Okay, can you see a green line here? Okay. Can you see a green line? No problem, no problem. I have ways. Yeah. Yeah. Okay, here. Yeah, one is thicker, one is okay. Green. Okay. Okay, so it will continue like this. Yeah. Okay. That is not okay. This. Okay, so green. Now, why we have this graph? Red is direct I/O calling system call. Green is something that you use a library call only. The difference is, it seems that it doesn't change at all for the execution time. Change a very little bit. And here, you can see that, wow, the execution time is like this and it drops. Because here, very clear that I'm increasing the number of bytes that I read in. Of course, the number of cores will be fewer, and the time taken should be decaying exponentially. Because I grow the buffer size exponentially. Now here, it doesn't change at all. Because why? Buffer I/O is something unrelated to the number of cores that you call. Because every time it just take 4K data, or even 1 meg data, I don't know what the buffer size, let's say it's 4K buffer. Every time it's grab 4K buffer, 4K bytes, a buffer, then it gives you the data, and then, it uses up all the buffer, grab another 4K. So that means what? That means no matter, let me clean up, okay. Come on. Wait, clean up, okay. So that means this kind of F-read, F-printf, Scanf, all kind of F starting with F code not fault. Okay? They are very worth calling because this already smooth out the efficiency for you. Well, not smooth out the efficiency. Average out the time that you will need. You don't worry a lot because you call many calls because it's already have buffer serving you for this purpose. And now let's take a look at another graph. Okay, another green line. And this green line is just straight. So what is this green line? This green line is printing the system time. The time that's spent inside the kernel. Okay, I can do an experiment and get it. So this is the straight line for the green one here. I don't need to color it, it's a straight line. Okay? So why is it straight line? Because it doesn't care how you call. I will do my own work. Okay, I'm the library. I win over you. Okay, you call me. I don't care about how frequent you call. I just grab 4K and try to export the data amount that you asked for. Okay, so here is not much difference. What are they? They are the time they spend on the user land, the user code, not the kernel code. Because user code, let's say that it needs to copy the data and put it in the screen, okay, or put it in the buffer. So they are more or less constant here. The green line and the red line, they linearly overlap. Okay? So although this is an extra, but this telling you that this kind of core is very good. And when we come back, I will tell you what exactly is EOF. Okay? Who think that I need a program. I want a program, okay, to read a file, and a file is an empty file. Who think that the empty file is one byte storing EOF. Now this is very philosophical. You call it an empty file, then it is empty. But you need a EOF, so this is not empty. And it's not empty, I can call it empty file. But this EOF declares this is empty, so it should be empty. And we go back. Yeah, paradox. Very philosophical. Whether an empty file is an empty file, whether we have a character called EOF, then hidden, yeah, you may think that, okay, we are being treated by OS again, not for the teacher, okay? But OS again, there is a hidden EOF character inside a file. So what is a hidden character inside a file? Wow, very fascinating. What is it? Okay. Later I will explain to you what exactly is EOF. Okay. And before